Hey everyone, and welcome to a rundown of derivatives and as they relate to position and velocity and acceleration. So we're going to continue with our conversations about applications of derivatives, and so we're going to take a look at an object in motion today. And suppose we have an object that's moving back and forth along a number line. So picture one number line, and you have a piece of string and you have a bead on that string and it's moving back and forth. Now that piece of bead might move along that string at different velocities along its way, or different speeds. So it might go slow and then it might speed up. It might stop and turn around and go back the other direction. Depending on how you're dragging that, it's going to either speed up or slow down. It'll have different speeds along the way, and it's going to at some point stop and turn around and go the opposite direction. Now, consider this specific object during the first 5 seconds of its journey. So we're going to have this equation, and suppose this equation here, t squared minus 2t plus 3, is the location along that number line. So it's position. So if we numbered that yarn with positions, with a 0, 1, 2, 3, this equation would tell us where it is located at a specific point in time. Okay? So this is kind of our beginning, and this is where we're going to start. So let's take a look at what this object would look like. So if this is a graph, this will give you an idea. If we take that function that we had and we graph it a little bit, here's what's happening. So this parabola is the model of the time and the position. So that's that S, that's that quadratic that we had for that position. And if you look at the number line, this is actually what the object is doing. And if you watch what's happening along that parabola and what that blue time position dot is doing compared with the green object, you can see that the object, and it kind of stops and restarts because it's only during this, 5-second interval. And if we take a look at what's happening, so the S value, the slider, the time is going between actually 0 and 4 here in this. So this is just the first 4 seconds. Now, if you watch it, you can see that the object speeds up at points, and it will also stop and turn around. And if you notice, as it is speeding up, you'll see that this position will increase, right? And as it moves to the right, that position is increasing. As it's moving to the left, the object, the position would be decreasing. And so you can kind of see this relationship between the straight line motion and our time and position as it relates to a coordinate plane with that quadratic being graphed there. So let's kind of summarize maybe a little bit more of what we see. So when the object is moving to the right, let's talk a little bit about what we see in our graph. Now, when an object is moving to the right, so here it goes, moving to the right. Oh, there we go. Now let's watch it. Moving to the right, it's moving along that quadratic, and then as it moves backwards, it's moving backwards along that quadratic. But I think it's more helpful if we kind of take a look and see what's happening, if we can see what's going on with t. So here we are, we're going to start at the beginning. So the object will move to the left a little bit, and then it stops, changes direction, and moves to the right for a little bit. And then it stops, seems to change direction as it's heading backwards. But we're going to ignore that because that's not actually part of our equation. It's just a function of Desmos. The timer t likes to go backwards. So as t approaches 4, the object moves backwards, stops, changes position, and then continues on to the right. And if I change the value of t here, if I change, if I were to make this go on a little bit more forever and change so t goes beyond 4, we would see that the object would just keep on moving to the right. So again, just ignore the fact that this timer goes backwards in time. That's not actually happening. So again, we start at 3, we move to the left, we stop, we change directions, and then we move forever to the right. So that's the motion that I want you guys to focus on. And you'll notice that the speed of the object can be modeled moving both to the right and to the left. But we don't know what direction it's going based on just the speed. And so we're going to introduce this concept of velocity as a directional value. So velocity can tell us not only how fast an object is moving, but what direction it's going. So here are a few conventions that we're going to be using throughout this unit. A positive velocity is going to indicate a movement that's going forward or to the right. A negative velocity will indicate movement that's going left or backwards. Now, speed is the absolute value of velocity and will not tell us the direction. it'll just tell us the speed. So when we talk about displacement, displacement is defined as the total amount of change from position 1, so wherever you were on that number line, to wherever you end up. Now, this is different than the distance that we travel, so keep that in mind. I like to think of it like this. When you wake up in the morning, your displacement at the end of the day should always be 0. Your total change, your amount of change that you've had from the morning when you get out of bed to when you go back to bed at the end of the day should be 0. Now during the day, you probably got up, you went to school, you went to the store, you went to work, you went places, you traveled all over. So your total distance traveled is a lot. That's more like, the steps on your watch when you have a step counter that'll tell you how many steps you've taken. That would be like your total distance. But your displacement is just at the end of the day, how far did you move? So when we talk about displacement, what we do is we want to take basically this notation, t plus delta t. Remember, the triangle means the change in t. So it's just basically your ending time, what's your position then, minus where you started from. That's how much you moved at the end of the day. So for example, if we want to find s of 0 and s of 4, and then find the displacement over the first 4 seconds, it would look a little something like this. First, we need to find s of 0, so I'm going to plug 0 in, I get 3, and then I need to find s of 4. So that's going to be 16 minus 8 plus 3, that's going to be 11. So my total displacement is simply s of 4 minus s of 0, so where I am now minus where I started from, that's just going to be 11 minus 3, or 8 units. So that's how far I have gone during these first 4 seconds. So now let's talk a little bit more about this velocity concept. So we also know that we can find something called the average velocity. Now we've explored average values of functions and average rates of change before when we talked about derivatives, and average velocity is no different. So average velocity can be found by taking the slope of the positions. So remember, this is my end minus where I started. So my ending position minus where I started over the change in time. So essentially, if we wanted to look at the average velocity from time t equals 2 to t equals 4, we already know that our position at time 4 is 11. Our position at time 2, and let's remember our equation, it's up here at the top, t squared minus 2t plus 3, so it'll be 4 minus 4 plus 3. So at s of 2, there we go, at s of 2, oops, that's already been squared. Our position here is also 3, so we're kind of right back to where we started from. So to find my average velocity, it's simply s of 4 minus s of 2. It's just the slopes between the 2 points. So 11 minus 3 over 4 minus 2, that's 8 over 2, that's 4. And then whatever our units are per whatever our time is. So I'm not sure, I can't remember, let's go back and see if it indicated any kind of units, because we always want to make sure that we include that. So we'll say units per second, because we don't know what our distance unit is being measured in. So 8 units was our displacement up there. 4 units per second is our average, and we indicate this by saying v average. So our average velocity over those 2 seconds is 4 units per second. Now, that's not necessarily going to indicate, like if I pick a time in there, that's not the velocity at a specific time. That is called our instantaneous velocity. And this is something we found before when we were talking about basic derivatives. It's the instantaneous rate of change. And the easy thing about this is that we now can use that shortcut that we've been learning with derivatives. We don't have to evaluate limits anymore to find instantaneous rates of change. What we need to understand, though, is that velocity is the derivative of position. Remember, derivative means rates of change. So the rate of change, how fast is my position changing? Well, that's a measure of velocity or speed. That's miles per hour, feet per second, units per second. So if I want to find the instantaneous velocity of an object, I need to take its position function, which again is t squared minus 2t plus 3, and I'm going to find that the velocity is just the derivative of this function. So it's just 2t minus 2. So if I want to find the velocity at t equals 3, I'm going to find s prime of 3. Now, when I do all these functions, it's really good to label everything. You never want to have an unnamed function, because in just a moment we'll be talking about acceleration, and acceleration is the rate of change of velocity, which means, you guessed it, it's the derivative of the velocity function. So we're going to have three different functions running around on our papers here. We want to make sure that we name them and label them appropriately so we don't lose track. So 2 times 3 minus 2 gives me 4 units per second. Now we got lucky in that the average velocity was equal to our instantaneous velocity in the middle. And actually there's a theorem that we're going to be learning later on that says that if we do have a continuous function, if we can find the average over an interval, somewhere on that interval, the instantaneous velocity or the instantaneous rate of change or the derivative will equal that average rate of change between the two endpoints. That's something called the mean value theorem, and we'll discuss it in another video. Now let's talk about acceleration. Acceleration is the rate of change of your velocity. So if we know that the velocity is 4 units per second at t equals 3, well then what's our acceleration? Because we know that our object is getting faster, and if I scroll back up to that Desmos graph, we'll see that the object speeds up as it's moving to the right. So the acceleration tells me how fast the velocity is changing. So it's the derivative of velocity, which means it's the second derivative of position. So if I wanted to know the acceleration of this particle at t equals 3, I would find the derivative of my velocity. So we'll do that here in a moment, but I want to point something out. Throughout calculus, calculus and physics develop side by side with calculus is the language of physics. And Isaac Newton did a lot of that work along with other people who contributed greatly to those fields. However, these gravitational constants that you guys use in physics, 32 feet per second squared, 9.8 meters per second squared, that's the acceleration due to gravity. And those constants were found by using this whole concept of a rate of change. If we can measure the position over time and gather data and build a model for that, we can measure the velocity. If we can measure the velocity, we can measure the acceleration. And we found that the acceleration of an object near the Earth is always a constant acceleration, barring any outside forces acting upon it, like wind or something like that. So that's a little side note. Here is our acceleration. We're going to find it for the particle at t equals 3. So if my velocity function was 2t minus 2, then acceleration is the derivative of velocity, and I'm going to throw this one in here. It is the second derivative of position, and when I do this derivative, it's just 2. Now there's no t to plug in, which means this is a constant acceleration. So this object has an acceleration rate of 2 no matter where. And so let's talk about our units then for acceleration. Every time we do a derivative, we add a per time. So remember, position was measuring units, velocity was units per second, so acceleration is units per second, or just units per second squared. Now, here it makes sense to write it as per second squared. It's not always the case, and we'll see that as we move forward and see some AP problems. So let's just kind of wrap up here with a couple of quick examples. Let's talk about dynamite. So, all these outlandish problems that we have. Here we have an example where we have a dynamite blast propelling a heavy rock straight up with a launch velocity of 150 feet per second. Whew. So that's my initial velocity. It reaches a height of this equation after t seconds. So it starts on the ground, s of 0 is 0. It heads up, reaches a maximum height, and then falls back down. We want to know, when does this rock reach its maximum height? So let's think about this. If my rock is going up, it's going to accelerate up, right? So velocity won't be constant. And then it gets to the top. And before it changes direction and comes back down, think about this. As it goes up, gravity is pulling it down and slowing it down. So as gravity acts on this rock, the velocity is decreasing, and at some point, that velocity reaches 0. And then the rock turns around and falls back down to the earth. So at the height, the velocity is 0, and then it comes back down and smacks into the ground. So essentially, if we want to find when the rock reaches its maximum height, we need to find what is t when the velocity is 0, okay? So here we go. I need to find my velocity. Well, the velocity is the derivative of this position function. So it's just 160 minus 32t. So I'm going to set this equal to 0. Anytime I approach a free response question, especially on the AP exam, I always want to make sure that I write down my thinking. Even if I don't know what the velocity function is and I don't know how to find the derivative, as long as I write down I'm looking for when the velocity is 0, that could earn me points on a free response. So now I'm just going to solve it out and get my answer and figure out what is the time here when the velocity is at 0. And so we find that t is 5 when that velocity reaches 0, and so that is the maximum height, so that's the time that we reach the maximum height. T is 5 seconds. Now that doesn't tell us how high the rock goes. We have to go back and plug that into our position function to be able to determine that. So now I'm going to go and I'm going to use my s of t, and I'm going to find s of 5. So 160 times 5 minus 16 times 5 squared. And we get that 400 feet is my maximum height. So it goes up 400 feet, turns around, comes right back down. Now, these are all well and good. We don't always get such nice numbers. So let's take a look at this one. What is the velocity and the speed of the rock when it is 256 feet above the ground on the way up? So we want to know what the velocity is at 256 feet. Well, velocity, my velocity function was a derivative, and if we look back, it was 160 minus 32t. And my position, notice all of these are in terms of t. So I can't just take this 256 and use it in the velocity function. I have nowhere to put it. But what I can do is I can figure out what t is when I reach a height of 256. So what I'm going to do to solve this is I'm going to put 256 right here, and I'm going to solve this function. Now, if I have a graphing calculator, it's super easy to plug it in and find the solution for a function like this. However, this is a primo non-calculator problem. So I'm going to go ahead and subtract the 256 over to the other side. I'm going to do a little rearranging. And then I'm going to factor. And I notice that each of these is a factor, or has a factor of 16. So I'm actually going to factor out a negative 16. That's going to leave me with t squared minus 10t plus 16. And when I factor this trinomial, I get t minus 8, t minus 2, which means at the times 8 and 2, I reach this 256. Now, I have to think about what's happening in the problem. It says, what's the velocity and speed of the rock when I am 256 above the ground on the way up? So I have to think about this. On the way up, on the way down. I need to use the earlier time. So I'm going to use t equals 2. So the velocity at 2 seconds is 96 feet per second. Now, what's the speed? Well, remember, 96 indicates that I'm going up. So at 96 feet per second, remember, speed is the absolute value. So the speed will be 96. Now, on the way back down, when I'm at v of 8, consequently, I think I'll also get I'll get 96, but I'll get negative 96 feet per second. So the speed in both cases, so this is on the way down, this is on the way up, the speed in both cases is the absolute value. It's just 96. So the velocity, that negative velocity, says I'm going downward. Positive velocity says I'm going upward. So that's how velocity is helpful. It gives us that nice directional indication. Now, let's finish out here with a couple extra questions. I have 2 more for us. What is the acceleration of the rock at any time t during its flight? Well, remember, our velocity function was 160 minus 32t. And acceleration is the derivative of velocity. So it's just negative 32. Oh, feet per second, and it's squared because remember, every time we do a derivative, we add a per second. So at any time during the blast, it's being acted upon by that negative downward acceleration, that acceleration due to gravity. Now, when does the rock hit the ground? Well, that's when we want to solve for the position. The height would be 0. So I'm going to use that, and let's see, we have 160t minus 16t squared. So when I solve this, I'm going to factor out a t, and I get two answers. I get t equals 0. Well, that's the initial time it started on the ground. And then when does it land? It lands when 160 minus 16t is equal to 0. We should get 10. So 10 seconds. That's a long time in the air. Who makes these problems up, right? So I hope this has been a helpful video for you to help give you an understanding, a basic understanding of velocity, acceleration, and position and how they're related to derivatives. My encouragement, as always, to you is to keep on going with this. Mastery is not at all expected the first time through. So as you're starting your assignments and doing your practice work, remember, it's okay to be challenged. We like a challenge. We don't grow without that challenge. So keep at it. You can do this. You've got this.